office has moved to the new building at Zhejiang campus, and most of you were moving to Zhejiang very soon. So we have something new, and maybe in the future that you can also come to my office. Some of you to read. Well, maybe I'm not at our office, but you can also come to my office since I have a large screen. But now I'm at home. Okay, so today Ben is going to lead the discussion on this paper. It's quite interesting. So yeah, Ben, go ahead.
Okay. Hi, everyone. Today, I'm going to lead this paper reading. The title of this paper is A Machine Learning-Based Approach to Clinopyroxene Thermobarometry Model Optimization and Distribution for Use in Earth Sciences. The first author is Jorgenson. Jorgenson, born in 1995, she is still a PhD student at University of Geneva, Switzerland. She is Canadian and got her bachelor degree at Dalhousie University in Canada. Her major is geoscience, and she is supervised by these two people, Karachi and Petrolate. And their research field are volcanology, magmatic system, and machine learning. So volcanoes are beautiful and dangerous, and also it's a popular research topic because they are active geoscience sample. Determining the structure of magmatic plumping system is an important part of understanding the volcanic eruptions. When we investigate the structure of volcano, we have to know how deep is the magma from and what's the temperature of the magma. Therefore, we need a thermobarometer. Classically, these thermobarometers result in a single equation, which links that specific mineral chemistry to the variation in pressure or temperature of crystallization. However, these formulas are often associated with large standard error estimates and are only appropriate for specific melt compositions. Early thermobarometer calibrations were self-validated, which means the data used to regress the model are also used to validate. This typically leads the data overfitting and underestimated standard error estimates. Actually, our recent work in the rat figures has proved it. We tested this typical Clinopyroxene thermobarometer, which is the NIMS and Teller 2000. It turns out that it has a bad accuracy when predicting other experiment data. It only has overall accuracy 41%. So developments in machine learning application to petrology by Petrolate 2020 and Thompson 2021 have resulted in a machine learning approach to thermobarometer. Both studies have proved that combining with machine learning, the thermobarometer indeed improved comparing to traditional one. There are two main ingredients. First, the people always add as more as data they can into the new model. The second is the machine learning algorithms are powerful to calculate complex situations such as geoscience. So in this paper, they collect data from two parts, downloading from a library of experimental petrology research database, and they also collect them by themselves. The unfiltered CPX Clinopyroxene data have 2571 raw data. The temperature is from 679 to 2180 degrees C. Pressure from 0 to 160 kbar. Then they remove the data pressure larger than 60 kbar, and some equivalent data. Final data set have 2079 rows data, which include CPX compositions, chemical compositions, pressure and temperature. The train test data split is the first problem this paper care about. The pressure temperature distribution of the dataset is not uniform. Experiments are frequently run at low pressures, so randomly extracting from the dataset unevenly with the test set to have low pressure experiments, which result in a poor representation of the standard error estimate. To solve this problem, the test data was uniform extract from the calibration data set on a graded sampling. That means they split train and test data set by data distribution interval, so you can get a balanced test data set. The green point here is the grade sampling result that shows in this two red circle. You can see there are many green one, but not so many black one. Black represent the random sampling. So basically, the graded sampling is better than the random sampling. So the algorithm they choose is random forest. Random forest is a machine learning method that employs decision trees to produce an improved prediction-based model. Using the results from a distribution of hundreds of trees to generate an output. In this model, the input is the chemical composition of the clinopyroxene. They didn't use temperature as an input parameter to estimate the pressure because experiments performed at high pressures are also performed at the high temperatures. That makes experimental pressure and temperature not independent. Then the algorithm built a random forest, which comprise many decision trees. Decision trees have many nodes to decide which way the data go. And in the end of the tree, there are the pressure or temperature numbers. During the output, there are three kinds of output way, which are mean value, median value, or mode value of those hundreds of trees. There are two hyperparameters they mainly test. One is the MRTY. MRTY is how many variables are considered at each node. Well, in this case, it is the number of major elements of clinopyroxene are considered at each node. Another is N-tray. N-tray is the number of individual decision trees. To test the effect of hyperparameter, they run 90,980 simulations, which encompass 90 combinations running from 1 to 9 MTRY and 101 to 1001 entries, where each is run 200 times with the respective test and train data. As we can see from these figures, the model has the smallest SEE when MRTY choose the 9. Yes, and the entry have no influence on the SEE. You can see from this figure. And when MRTY is 9, the density of zero residuals are the largest. The residuals means the difference between true value and the predicted value. So if the zero residual density is larger, the model will perform better. And the second thing affect the model is the output way. The mean and the median way show better SEE and R square. Though the mode way have the largest density in the zero residuals, but it shows poor residuals at higher values, which you can see from those two red circles. The green one is the mode, output way. And besides, the major elements of partitioning within the crystal structure of clinopyroxene is not solely sensitive to pressure and temperature, but also depend on the chemical availability of elements in the residual liquid, which is the melt phase. Generally, when adding liquid data in, the model gets better performance, but the main purpose of this paper is building clinopyroxene along thermobarometer. The liquid add part is just additional discuss. So for considering the natural samples predicting, they perform a model experiment for sparse data. These are results from a model with a pressure gap from 5 to 15 kbar forced into the data set. It's a part between the two gray dashed lines. And the purple represents the mean value, blue represents median value, and the green represents the mode value. We can clearly see median and the mean models perform better from this figure because they can close the gap by averaging the values, and the median performs the best in this experiment. So the author suggests that all users adopt a median value for the pressure and temperature estimates. The samples plotted here are 200 times estimates given from one forest for one sample. The solid black vertical line is the estimated pressure using the median method. The solid red vertical line is the true pressure, and the two black vertical dashed line represent the IQR. The IQR is the interquartile range of the voting distribution, and there's a figure to explain what is the interquartile range. Basically, when IQR is large, that means your data is distribution. Your data distribution is dispersive, and when IQR is small, the distribution is concentrated. Therefore, the IQR is smaller. The result of the trees are more concentrated, and you can get a better estimate. The IQR system is specially used for the median output model. And also you can see from these three figures results that if the IQR is ln kbar, you get the perfect estimate pressure. And if you get a largest IQR, you get a largest residuals, which is the true values, the difference between true values and the estimate one. So the final part is the arrow bar in the grid. The gray points represent the IQR range, and the points in green represent the data removed any IQR larger than 7 kilobar. So the IQR system indeed improves the median output model. Okay, that's some take-home message. This model has an SE of 4.4 kilobar, 76 degrees C, and can be applied to a wide range of compositions. Given the right considerations, this model can result in a high-resolution study of crystal magmatic systems. It also provides a general strategy for a machine learning approach to a single-phase thermobarometry, which can be applied to other minerals. And there are some comments from me. And first of all, I want to say is this paper is more like focused on a tool, which is the thermobarometer. And for now, they didn't apply this model on any natural data, which is to predict any data without any experimental pressure and temperature. So it's just a tool. And but there are two parts I'm interested in. Is the first one is the IQR of the voting distribution because they consider this part to equal to the data distribution, and it's easy to understand what they are doing, what they are doing for improve this model. And the second part is their model is really user friendly because they write a lot of part for the instruction and tell people under what situation you should use which kind of the script, and they provide all the scripts in the website. So and there are many details in this instructions. So I think it's pretty user friendly, which any user can use it. But it's for our code. Yeah, that's all. Thank you.
Okay, thank you, Ben. So questions from our participants today?
Hey, Ben, it's Brian. Thanks for the summary. Since you like the IQR part, can you explain it further? Mainly, is the IQR output by the machine learning model? So does it essentially output a mean prediction and then also the interquartile range together with the mean output? Or is the IQR something that they quantify afterwards?
Well, because there are many decision trees in my forest, right? Like they tested that there are 201, and they use this IQR of each tree's results, that there are 201 results there, right? So they test this IQR IQR value, that if you get a large IQR value, that means there are not many your median output is not representing all the data, right? So if you got a zero IQR, that means like many results is equal to the median. So if you use this median, that can represent all your results, all your trace results. If the IQR is too large, then that means not many data are equal to your median that you use.
Right. So it's essentially measuring, in a sense, the uncertainty in the prediction, right?
Yeah, right.
So our higher IQRs, how does that compare to the distribution of the residuals? Higher IQR is also correlated with higher residual errors. I think that might be your next slide 15, slide 15.
Yes. They tested it by this experiment, and yes, they get this result that if you have large IQR, then your estimate is far from the true value.
Yes, well, not super far, actually. I mean, if
you
think of if you think of an IQR as like a standard deviation, then that's a really high IQR, and the difference between true and estimated is still very small. So I'm just curious to see how IQR from essentially an ensemble of decision trees, how that compares with like a rigorous statistical measure of uncertainty.
Yes.
It's interesting usage of it.
But I think for me, it's my first time to know that you can do a thing like on the result of the many trees, in the forest. So it's kind of, a new thought. So, but maybe it's not really useful for the improvement of the model.
I'd say it's very useful. Like if it's very if it's fairly similar to what you get with some kind of uncertainty quantification, then I'd say that's very useful, because in general you always want an uncertainty with a prediction. And
right.
Also, it'd be interesting to see how much IQR changes versus their number of trees. Like, does it essentially reach an asymptotic value as you increase the number of trees, or do you get basically the same IQR with the lowest number of trees?
Right.
Yeah.
Okay, I will continue with this, with a question on my end. Probably I didn't read as carefully in details that do they consider the analytic uncertainty to take into account of the uncertainty that causes the result? Basically, all the input values have uncertainties because you cannot measure all the concentrations very accurately. So it's inevitable that it will produce your result or output, which here is a pressure, with a certain uncertainty due to your analytic uncertainty in the input. So did they try that?
Well, no, they just they didn't consider that the experiment error, the compositions. They just used the composition and the pressure and temperature. They didn't consider about the error in the experiment.
I think that's another interesting thing that they could compare, because basically for every element there's analytical uncertainty. Some are bigger, relatively speaking, some are bigger, and some are smaller. And then if they do Monte Carlo simulation, and then basically we assume, for example, normal distribution, whatever, and then you do that 500 times, and you look like the output, and then you can just take account of that by running exactly the same model to look at how the IQR evolves. So maybe if my random guess is interesting, is that maybe the input value uncertainty is as large as the figure C, as you are showing here, assuming everything is the same. I don't know.
Are you saying through, when you say running a Monte Carlo simulation through the model, through a decision tree model, or through a physical empirical model that he showed earlier?
Through this random forest model.
Oh, okay.
Because you have 10 input values, and each input parameter has a certain uncertainty. So say you have the for example, MGO that's like 28%. Actually, that's the analysis, and the truth is that it could be anything between 19 to 21. So then you assume there's a normal distribution with a mean value of 20, and the minimum is 19 and maximum 21, and then you have increment, for example, 0.1. Let's say that's the detection limit of this element. Then you have this normal distribution, and then you do the Monte Carlo sampling for 100 times. Each time you randomly take a value from between 19 to 21. And you do this for every input parameter. And of course, that will produce slightly different results, given exactly the same random forest model. So that
I would expect it to give
So that also shows that how the analytic uncertainty on the input will affect the output. Maybe for a lot of models it doesn't matter, but so for some models it matters a lot, because that means some of the values that are quite important. Some of the input values parameters that are important to the output have very large uncertainties. Of course, they're going to affect output dramatically. So I think in this case, probably they're okay, because they're measuring those, let's say, oxides that is relatively accurate with a relatively small uncertainty, relative uncertainty. So they probably should be fine, but I think it's good to test. I have another question, Ben. So to your interpretation, if they're doing this way, what's the advantage or what the different information we can get compared with a random forest when people put like say fishing importance or something like that? So what's new we can get from this compared to the, like say we just do the random forest, so we just know the fishing importance. What's new information we could get through this method that we cannot know before?
I think that like just like the Brian saying that the IQR system is good at using when you check the predict result, if the predict how the predict the results behaving, that there are some bad predict or that there are some good predict. And if you have a 0 IQR, if the predict result have a 0 IQR, then that means all your decision trees you can get a good result from all your decision trees. Then I think maybe in that situation, all the decision trees maybe they are in a same format that maybe equal to that this 200 or hundreds of decision tree have the same feature importance, that which means that feature importance is have more accuracy. I think you can trust it more, but they didn't discuss about the feature importance in this paper, so that's all my thinking. So if you have a good quality of the predict, which means the IQR is smaller, then you could use that feature importance to explain more about the geoscience or something. That's how I think.
I think also, well, I'm not sure if your question was just in terms of random forest in general versus decision trees. But if it is, I think people have found just empirically that if you have a bunch of decision trees and then combine their predictions, then you end up getting a better prediction. I think that's essentially, that's a machine learning technique called bagging, I believe. So you have bagging and then you have boosting. So bagging is essentially combining a bunch of weak learners, where a weak learner would be a single decision tree. So the random forest should, in essence, give you a really good prediction. So independent of the uncertainty quantification, just using the random forest should give you a better prediction, because it's you're just essentially getting a more expressiveness in your prediction by combining a bunch of random a bunch of decision trees. And yeah, like you said, then I think the IQR is an interesting extra contribution to it.
Yeah.
Okay, Ben, you will continue to talk more about the limitations of this work in terms of the application to the natural samples, because in your case that they cannot apply to very deep, at least so far.
Yes, right. Because there are a small data set about the high pressure samples. You can see there are about like 500 data, and the data set is smaller than 500 because there are other filter things they use. So their model is is not fit on any data larger than 30 kbar, and besides they use all the experiment data they use are from all kinds of experiments. So the composition in the mantle is different from the crust. So the mainly experiments data they use are from the crust experiments. So the composition is different and the temperature pressure is different. So it's hard for me to use to predict the mantle pressure and the temperature. So mainly the composition problem, I think. So or maybe we should still build a new Clinopyroxene thermobarometer used for the mantle. Yeah, although they think their composition is wide enough, the range of their composition is wide enough, but it's not for the mantle. It's just for the crustal magmatic system. Yeah, that's a problem that for us to use. Yeah.
Okay, any more questions from our participants today?
Yes.
So Wumi is asking whether, I just read it aloud so that maybe it's the recording is easier to do that. So can you explain the grid search sampling method?
Yes. So first, why they use this grid sampling, because regression, the machine learning regression method, you have to like when you test your model, you have to have a balanced test data set, because you can't focus on the like lower pressure or a large pressure. But in their case, they have more samples at lower pressure. They set have more lower pressure data. So you can't, if you random sampling, you will get more lower pressure data in your test data set. So for getting a balanced test data set, you have to like for each interval, you have to choose some percent samples of all data in this interval, that you can get a more balanced data set than the random sampling. I don't know if it's clear to, I have explained it clearly. If it's clear. So the specific way I think you should check our code, that I only can explain how it's going, but the specific code you should check it, our code.
Without knowing the code, I'm gonna guess that they might have binned the samples like in a histogram, and then maybe choose evenly from the bins, and maybe that way it's, so like a bin is essentially a grid cell. Maybe that way it's more evenly distributed, as opposed to just the raw points. You can pre-bin it into a histogram and then choose that way, but I might be wrong.
Yeah.
Okay. Thank you, Beth, for the discussion. Thanks, everyone, for your participation. Then let's see the speaker on Wednesday to explain more about her work. Maybe not only limited to this paper, I hope. Okay, have a good day, everyone.